All right, everybody, this week I elected to go ahead and do all the welding ahead of time. That way we'd have all these examples like this one, some broken ones, a whole bunch of tensile strength test ones, boom, just like so. A whole bunch of examples that we can go and look at. So I spent a good deal of time welding, so we can look at all these different examples. So let's just start off with the one that's still together. Nice and simple. This one has some defects too, as you can see. Slag pocket right there. That is a surface of slag that's still slag in there. I could chip it out if I wanted to. There's a bit of slag left on the surface of the weld. Just like so. So that is a slag pocket. Back here at the bottom, this we would call that a little bit of arc blow. So just to give you an idea, this weld was done, 170 amps. I would say 18 volts. I didn't catch the data, but I would guess about 18 volts. 7024, electrode 724, so quite strong. Decent size, mildly asymmetrical, not bad. See, it walks out a little more on the flats here, maybe a little worse than I thought looking at that camera shot. Walks out on the flats a little more than up on the top. Be good for a 3/16 inch weld. This thing is probably just a little heat layover. Discontinuity here would be a slag pocket, a pocket of slag on the surface. And this one here, would be a little bit of arc blow. Arc blow is just where that arc gets kind of loud towards the end. You end up polarizing the plates. I did this in DC electrode positive, and as I was finishing up, it just kind of blew that end out a little bit for me. Not as much material there on the end. That's where I started. Took that weld, took one of those welds anyways, and broke it. We can now start looking at some of this interior volume. You can see plate deflected quite a bit before it let go, which you'd hope for. You'd expect something like that. Wasn't a beautiful weld, I can't say, but decent enough. Let's look at some defects that are maybe interesting to see. So first off, let's look at this. You see that real woody kind of grain? That is actually beyond the heat affected zone, and now I'm starting to rip up the base material. That's actually the base material. And you can see that right here where it's actually coming up out of the base below the plane on that outside edge of the heat affected zone. These little balls right here, since it's a triple pass done with 6013, 125 amps, this would be spatter. That's another defect. So far, slag pocket, spatter, arc blow. Looking at the bottom here, any number of things going on. This is actually a slag inclusion, and it's not there anymore, so it's a little hard to see, but that little root right there, that little shiny zone, that's where slag used to be, but it fell out. And that was right at the root of the weld. That's why commonly you would do a weld, grind out the root of the weld, and then go back at it again to get all that out of there. This is what happens when you don't properly preheat. If I were to preheat this, now this would go away. So this is a function of the slag going to where it's cooling. It ends up collecting right in there just like that. Hoping to see something a little bit more, but I don't. Doesn't mean my weld's perfect, it just means I don't see any great examples of things I want to show you. Kind of interesting here. You see this little edge right here? How it's all shiny, but it doesn't go very deep. Every time you weld, the grains get a little bigger and a little bigger and a little bigger. This is all grain growth in here. You can kind of see the size where as they go. And so what happens from this dull area here to this shiny area here, this is from me water cooling that last weld. Didn't want to wait anymore. These I let run hot. This one I water cooled, and you can see that kind of surface hardening of that material. Single pass that I broke. I believe I have a couple of those. Yeah. So common. Again, let's look at that little slag inclusion. Now I said slag twice now, but with a different qualifier. This is a slag inclusion. It is included in the weld. There's some more of it right there. That's slag inclusion. And this is actually due to the fact that this lower plate's a heat sink, and that's what draws it over there. Weld looks okay. A couple little areas where it comes down really abruptly. This one right here comes down really abrupt. They would call that overlap because that's not really good fusion right there. That's just that weld metal sitting on the deck. A little bit of overlap. Again, seeing this, actually these were AC, so you don't see it so bad. But a little bit of that arc blow at the end. Again, that's just from polarizing those plates. When you polarize the plates, rather than attract that droplet, it actually repels it back up and up and up. And that's that repelling of that droplet that helps it dig out that material accidentally. It's not a helpful thing, so maybe not the right word there. But every so often you're going to get a little bit of gas in these welds. Water, oil, paint, zinc, any number of things that can burn off and form a gas. Now it seems like they would just get out of the way, gas would escape, wouldn't be a big deal, but every so often it gets trapped. We have this right here. It's kind of a different look. It's a very teeny one, but it's still the same thing no matter what. Whenever you see a really, really, really little shiny, my eyes are pretty bad, but a little shiny divot like that guy right there, that's gas. That little guy right there, that's gas. You can see it's kind of different than the rest. It's a little bubble. Again, a little bit of that cooling zone that you're seeing there going on. If I were to weld, remember if I had my two plates together and I were to come in too steep, I could have cut the top off. That's called undercut. We went over that in an earlier lab, I believe. Commonly, you come up with a product and you're saying, I'm going to make this product in X, Y, and Z in this sort of this pattern, this way. And then you make it, and then what you do is you test it. So these, I'm saying, look, this weld's strong enough that I can put a great deal of force. This actually weld is designed to fail, by the way. These two come together. There's an open crack, and when I push down, it just lifts that crack up. If I were to weld this back edge together, this wouldn't happen. Or if I had a full penetrating weld, that wouldn't have happened either. So this weld is actually designed to fail. It's called the fillet break. Let's move on a little bit. Let's look at things put into tension. So I took a couple of pieces of 14, 16 gauge, I believe, 16 gauge hot rolled A35 steel. Did a double braze on them. This is actually done with an oxy-fuel torch. You can see those little ripples there, oxy-fuel torch. You can also see a little bit of the heat pattern, how far that heat went out. Boom, boom, boom. I put the sample in, and my joint won, and the plate failed. Just like so. Now contrast that with TIG welding, or not TIG, but MIG welding on some smaller stuff. Broke right at the weld. This caused the plate to fail. I mean, part of that was my bad stuff, I would guess, on that one. And this one I kind of took the effort to make sure it got it good. So this is brazing. Kind of interesting what happens here. These two materials, I mean, they didn't start off exactly the same, you can see, because this one was a little bit shorter. But as they pulled down, they didn't exactly start off with an hourglass shape in them either, right? That is part of going through the braking process. So we put this thing in a tensile strength tester. That's pulling it apart. This process goes through as the material. So this is that stress strain curve. I'm gathering my thoughts as I go through this. Stress strain curve. This is where the load comes up, hits the point where the material begins to yield. As it yields, it doesn't go up anymore. It just plateaus, and then suddenly it drops off. So it yields. It goes through a deformation. So plasticity of the material here. In this particular process, it goes through elongation, would be our particular deformation. And that's why you're seeing this necking down. This is the tensile strength tester stretching this thing like a piece of gum. Then eventually it reaches a point, temperature rise and whatnot, causes a yield, fracture, boom, off to the races. So that's the example you want to see. I did that on some thinner stuff. And you can see a little too much heat. You can actually see that from the rainbow on the back, just how far I got that heat to go. A little too far. So this is more of that heat affected zone. I'm guessing I got a little too hotty with brazing. I probably caused a little bit of melting of the base material. Fails at the weld. This one here, again, another brazing, improper machine setup. Just so you can see, they look probably something like that. I don't know if I'm getting that right now. Let's go with something like that. Boom. Had good penetration. Too hot. Let go. Really common. You're going to see that with wire feed. So this is 18 volts, 187 inches per minute of wire, argon CO2 cooled. Just give you some of the numerics so you know what we're doing here. This one probably could have held on a little bit longer, but it propagated that tear, and then that tear just went across. Bang. That's why you got this funny little rip off. But that tear is at the toe of the weld. That's where you're always going to see a heat affected zone failure. Remember, heat affected zones, not the weld, not the original material. It is the material that is affected by the heat. So going down to some thinner stuff now in both categories. Common, you're going to see that heat affected zone tear again. Boom, just like so. Not the prettiest of weld either. Ooh. And then again, back to the brazing. So brazing does pretty good. And why does brazing do better than the others? When you get into thin material, brazing does really good because brazing does not melt the base material, and that is key. Don't melt the base material, you don't make any martensite formations, you don't have that heat affected zone, doesn't make those tears hopefully, and that's where you see brazing's very, very good on thin materials. So, kind of recapping all this, these are destructive tests. That means we destroyed everything. And you can have to do that. We pretty much hold the automotive industry to the same level, right? Make us a car, show us that it can crash well. We're going to run it into a wall now. Very, very, very common. That's what they do. So, that's how that whole thing plays out. We weld it, we come up with our design, we weld it, we break it, we look to see how it breaks, we improve it, we'll see how it breaks again. A little bit later on this week and early next week, I'm bringing it into welding procedures, welding qualifications. Actually, I have a rudder head that I'm working on for those sailboats that I commonly race, and we need to update to the next generation of rudder heads because we're having a great deal of failure. So we'll show you how that works out. We don't have to break it. We could conduct the simplest of tests, which is a visual test. Hey, this looks good. That, not so much. Since this is less than 1/4 of an inch, we're going to say this passes underneath the guidelines I just generated in my head. That's one way you could do that. Beyond visual testing, what can we do? Well, we can gel this thing up and we can ultrasound it. So just like you look for a baby or anything else, we can gel this thing up, shoot sound waves for it. Sound waves come back nice and clear. We know there's no voids. Sound waves come back not so clear. There's voids inside of there. We could take this thing, put a bunch of special magnetic particles on top of the surface here, put this in electromagnetic field. They would stand up anywhere there was a void. So we can see them very, very easily. Aluminum is really prone to something called hot cracking. Hot cracking is a crack that forms when it's cooling, when it's solidifying. Aluminum has that problem, so what do we do for aluminum? Throw some penetrant dye on it. The dye will then wipe in. You dump the dye on the surface, wipe it in, go back with a towel in a couple minutes, dry it off, hit it with a fluorescence light, and it will light up any place that the dye seeps into a crack. Just that simple. Any divot, it's going to light up. So that's penetrant dye. If we want to look at something, this is really, really common in the oil fields. This is common in the gas line industry, fracking and whatnot. High pressure vessels where you just can't go around breaking everything. They would x-ray them. Take this, set it up, and shoot x-rays through it. That will tell us really good if there's any voids. Won't necessarily, I mean, it could help us to see some martensite formation and some other carbon deposits if you really get somebody who knows what they're doing, but for the most part, they're just going to look at voids. Fairly simple drill. Usually in lab, we would perform at least this. And then we would also, which is brazing. This is brazing with a torch, by the way. And then we would also perform that brazing on the thicker. and obviously the fillet brake. Most common process is fillet brake, tensile strength testing, just to see how strong is your weld going to be. So that's it, rather short video, lots of setup, lots of welding to hit all the defects. If you have any questions, make sure to hit me up. Last week we will be talking about we will be going over some final welding procedure, and we will be covering any of your questions that you have. Everybody have a good day. Talk to you soon. Bye.